temperature only. Remember, delta U, whatever we studied in the previous class, it is also function of temperature. That is mCV into delta T. Remember, that is a standard formula for change in internal energy. Okay. Next, in the second law of thermodynamics, we discussed all heat refrigerator, pump, heat engine, Clausius statement, Kelvin Planck statement, Carnot theorem, etc. So, second law of thermodynamics gives a new definition called as entropy, represented by symbol S. Okay. We know that all the thermodynamic properties are point functions, hence entropy is also a point function. Okay. In the previous class, we discussed about how to get the entropy change for various process. For general process in terms of T and P, next T and V and P and V. Okay, so go through all the derivation properly. Try to understand those derivation because the most important derivation. One derivation carried 10 marks, hence go through all the derivation properly, analyze properly. Okay, so once you understand the derivation, then easily we can do the numericals. Okay, today one more derivation is left out, that is entropy change during polytropic process. Okay, in the yesterday class, we derived the expression for entropy change during constant volume process, next constant temperature process, next isothermal process, okay, and then adiabatic process. Okay. Whether screen is visible, all of you?
Yes, sir.
Okay. Okay, this is the polytropic process. Today we are going to derive the expression for entropy change during polytropic process. Meantime, you should know the nature of curve polytropic process in TS diagram. So here the y coordinate indicates temperature and x coordinate indicates yes. Okay, and the nature of curve you see, so it is same as that of PV diagram. Only in case of polytropic process, the nature of curve for PV and TS remains same. Okay, you should remember, keep in mind. Okay, so whatever nature we got in PV case, same thing we are getting in TS diagram also. This is the nature of curve for TS diagram. Okay. Now consider 1 kg of consider m mass of gas, m kg of mass of gas being expanded by a polytropic process. Already we studied expansion and compression process. In expansion process, both pressure and temperature decreases, and in case of compression process, the pressure and temperature increases. Okay, now we'll derive the expression for entropy change. You see the first equation. Okay, we know that from the first law of thermodynamics, Q equals to delta U plus W. So whenever a process undergoes change of state, the first law of thermodynamics is given by Q equals to delta U plus W. And whenever you are writing in the differential form, we are going to write like this. Okay, dq equals to du plus dw. Okay, this is a differential form of first law of thermodynamics. Next, dq put as it is, and I say du always you have to take mcv into dt. This is called as actually Joule's law. We are going to learn in last module, that is ideal gas and real gas. I'll explain how it is a function of temperature only. Okay, du is mcv into PT. This is a standard formula for du. Like that, we are having one more property called as H, enthalpy. The enthalpy is given by U plus PV, and another formula for enthalpy dH equals to mCp into dT. So these two formulas you should remember. Whatever process it is, whether it is a constant temperature, constant volume, constant pressure, adiabatic or polytropic, whatever process. So du, that is the internal energy, is a function of temperature only, and it is given by the formula mCv into delta T. That is the formula for du. That is change in internal energy, and plus dW. So we anyhow we studied this dW in case of work done. Okay, that is nothing but PdV. This is a standard formula for dW. du is mCv dt and dW is PdV. Okay. Next step, divide the throughout by T, temperature T. Okay, starting we have to write like this: dq equals to mCv dt plus PdV. Next step is divide throughout by T. Okay, so dq by T equals to mCv into delta T dt divided by T plus P divided by T into dV. Okay, how we are getting P divided by T into dV means sorry, next step. This is our equation. Okay, here in this equation, what we are going to do? Just dividing throughout by temperature. Okay, we know that dq by T is ds. Okay, in the previous class we discussed that ds is always given by dq by T. That is the standard formula for entropy change. ds is dq by T, and you write as it is mCv into dt by T, and just you P by T equals to mR by V. We know that ideal gas equation equals to PV equals to mRT. Hence the ratio P by T becomes mR divided by V. Okay, so just you replace the term P by T with respect to mR by V. Okay, PV equals to mRT or P by T equals to mR divided by V. Okay, and you write dV as it is. Okay, next we are going to integrate this equation between the limits 1 and 2. So S1 to S2 integration of ds equals to mCv integration of dt by T between the limits T1 to T2 plus mR integration of dV by V between the limits V1 to. Just after writing this equation, integrate because we are going to take the two change of state. Okay, from state 1 to state 2. That's why we are going to integrate between the two states. Integration of ds equals to mCv integration of dt by T plus mR constant term integration of dV by V. So integration of ds is nothing but S2 minus S1, final entropy value minus initial entropy value, because it is a point function and also thermodynamic property. Hence it is a exact differential. You have to write integration of ds as S2 minus S1 equals to mCv. Integration of 1 by T is nothing but ln T2 by T1 plus mR ln V2 by V1. This is the equation for entropy change during polytropic process. Okay, so you have to remember this final equation, because sometimes they may ask obtain the value of entropy change during polytropic process. They will give all the value T1, T2, V1, V2, m value. All the value they will give. Only you have to find out the value of S2 minus S1, and it is in terms of T2, T and V. Okay, whatever the expression is there. Okay, this is the expression for the entropy change for polytropic process in terms of temperature and volume. Okay, so next now, so we have to express in terms of pressure and volume. So for that, what we are going to do? Okay, we know that P2 V2 equals to mRT2. So T2 equals nothing but P2 is P2 V2 divided by mR. Okay, just you replace that term. Okay, so starting we derived expression in terms of T and V. Next we are going to derive in terms of P and V. For that, what I am going to do? S2 minus S1 equals to mCv into ln T2 by T1. T2 is nothing but P2 V2 divided by mR divided by T1. T1 is nothing but T1 V1 divided by mR. Okay, plus mR into ln V2 by V1. Okay, so just you replace the term T2 and T1 by P2 V2 divided by mR divided by T1 by P1 V1 mR. Okay, so that we can write like this. Next step. Okay. So here MR gets cancelled, and after cancelling the term, you have to write this equation: MCV ln P2 V2 divided by P1 V1 plus MR ln V2 by V1, because the term MR gets cancelled. So next step, MCV ln P2 by P1 plus, you write as it is. Okay, you can write in this format. Okay, because V2 by V1 is there, and here also V2 by V1 is there. Okay, you can write in this format. Here first term only you have to take MCV into ln P2 by P1, and you can split and add. So M into CV plus R ln V2 by V1, because V2 by V1 is there in both the terms. Okay, so you take M into CV plus R into ln V2 by V1. Okay, we can rewrite like this. We know that I said you have to remember a certain formula. One is gas constant R. It is the difference of Cp and Cv. R equals to Cp minus Cv. So Cv plus R is nothing but Cp. So just you replace the term Cv plus R with Cp. Okay. So S2 minus S1 equals to MCV ln P2 by P1 plus MCP into ln V2 by V1. So this is the entropy change during polytropic process. Okay. And it resembles whatever I derived in the beginning. I think both are same. Just check it out. Okay. General equation. So whenever particular process is not mentioned, in that case, you have to use this formula, and also for polytropic process. Okay. And remaining, we are having standard formula. You can use those standard formula for constant temperature process, isobaric process. And suppose if in the problem the process is not mentioned properly, in that case you have to use this equation, general equation. Okay, that equation what I am deriving, this holds good for general process as well as your polytropic process. Okay, I think these are the values what we derived, same thing. Next, in terms of pressure and temperature, okay. So what you are going to do? MCV ln P2 by P1. Once again, you see, you can take this equation only. So S2 minus S1 equals to MCV ln P2 by P1 plus MCP ln V2 by V1. Okay, V2 by V1 here I am going to replace, because I want to express final equation in terms of P and T. For that purpose, you replace V2 as MRT2 divided by P2. Apply the equation P2 V2 equals to MRT2. So V2 equals to MRT2 divided by P2 divided by P1 V1 equals to MRT1. So V1 equals to MRT1 divided by P1. So you can write like this. Next step, see, you can rewrite MCV ln P2 by P1. Okay. Plus MCP into ln, you can write MR gets cancelled. So you can rewrite like this: P2 by P1 into P1 by P2. There is no change in equation. MCV ln P2 by P1 plus MCP ln P2 by P1 into P1 by P2. Okay, next MCV into ln P2 by P1 plus you have to split this term. Okay, I can rewrite like this: MCP ln T2 by T1 minus MCP ln P2 by T1. So both are having the same meaning. Okay, you can write MCP ln T2 by T1 minus of MCP ln into P2 by P1. Okay. So next, I am taking minus. You see, in all the equation here, first term contains CV, second term contains CP. Okay, third term contains CP. Okay. So now I am taking the P2 by P1 is there. Okay, so you take the common term. The first term and third term contains the ratio P2 by P1. Okay, I'm adding these two terms and putting in one format, like minus M common, CP minus CV. Okay, because it is a plus here, you take first term and third term. So minus M, you take the common in the bracket CP minus CV, because it is a plus. Minus into minus plus. into ln P2 by P1. So take first and third term, rewrite the equation minus m into Cp minus Cv into ln P2 by P1, and you write the second term as it is, second equation as it is. That is plus mCp ln into T2 by T1. Okay. Next, S2 by S1 is nothing but change in entropy. So first I am writing the second term mCp ln T2 by T1 plus mr. Okay. So here, as I said, gas constant R is the difference of uh, specific heats. Okay, Cp minus Cv is nothing but our general gas constant R. Okay, and here minus is that, here plus is there. Okay, then you can change the ratio. Instead of writing P2 by P1, you have to write P1 by P2. Okay. So mCp ln T2 by T1 plus mr. Cp minus Cv is nothing but mr, and I change the sign minus to plus, and I change the ratio also. Don't write P2 by P1. Suppose if you are taking minus, in that case you write P2 by P1, and suppose you are taking plus, you have to write ln of P1 by P2. So this is the standard equation for entropy change during any general process and also for polytropic process in terms of P1 and P1, P2 and T2. These are the three equations. So whatever equations I derived, the most important equation, and also you have to go through the nature of TS diagram. Okay, I repeat once again. So what are the nature of curve you are getting in various process? Okay, first process is your constant volume process. See the nature of curve. You have to show the curve like this, TS diagram. So second one, constant pressure process. The nature of curve is similar to our constant volume process, nature of curve. And the third process is isothermal process. So here isothermal means temperature remains constant. We have to show the horizontal straight line in case of isothermal process for TS diagram. And fourth process is adiabatic process. As I said, you'll get the vertical straight line. How we are getting the vertical straight line means, so do we know that ds equals to dq by t? Dq is 0, and you have to integrate both sides. Integration of ds equals to integration of 0. S2 minus S1 is constant. That's why you have to represent the vertical straight line for adiabatic process and horizontal line for isothermal process. And finally, we are having polytropic process. You remember the nature of PV diagram and TS diagram remains same in case of polytropic process, because both temperature and entropy vary, um, and also pressure and volume vary in case of polytropic process. Hence, you have to write the same nature of curve in case of polytropic process. So vertical straight line in adiabatic process, horizontal straight line in case of isothermal process, and curve whatever I shown previously in case of isochoric and isobaric process. Okay, so these are the most important things you remember. So don't forget the nature of curve, because the same thing we are going to continue in the applied thermodynamics. Okay, these are the basic things. So keep remember what is the formula, what is the entropy, what is the change in entropy for various process, what is the nature of curves. That's why you should remember 5 PV diagrams and 5 TS diagrams. So 10 diagrams you should keep in mind, nature of curve, and also for expansion and compression. Okay, expansion, whatever diagram it is there, it is for expansion. Compression, so if compression is there, you have to take starting from 1 and here ends at 2. That is compression means pressure and temperature increases. For expansion, it decreases. Now, okay. So next concept, I'll go to Clausius theorem. Okay, the most important concept in uh, entropy chapter. Okay. So every time they used to ask Clausius theorem. Okay. First, you should You should know the statement of Clausius theorem related to entropy. When a system undergoes a complete cyclic process, the integral of dq by t of around the cycle is less than 0, and mathematically cyclic integral of dq by t is less than or equals to 0 means you should remember this formula. Okay, already we studied the cyclic integral of any property is 0. Okay, cyclic integral of dv is 0, cyclic integral of dt is 0, and cyclic integral of dp is 0, like that. So cyclic integral of dq by t is nothing but cyclic integral of ds is always less than or equals to 0. Okay, it's never greater than 0. Okay, because it is a property. Cyclic integral of dq by t is 0. Okay, whenever it undergoes a cyclic process, you analyze the diagram here. Okay, so whenever they ask prove Clausius theorem, okay, don't make confusion. There are two things comes into picture. One is Clausius theorem, okay, and second one is Clausius inequality. Okay, so these are the two important terms, and every exam they used to ask these two theorems. One is Clausius theorem and one is Clausius inequality. Now first I am explaining the Clausius theorem. For Clausius theorem, this diagram you have to draw. Okay, so this is the PV diagram, and we are having a, you see, first round structure is there. No, this is the one reversible cycle. Okay, any process, just round structure you have to draw. Then after that, so first you have to write p and b, p as y coordinate and v as x coordinate. You have to practice this diagram. Okay, first you draw this original reversible cycle, whatever the round structure is there. This is original reversible cycle. Then after that you have to draw these lines. Okay, you see, so these lines are there, curved lines, you see, one two, these lines you have to draw. Okay, cutting the original cycle like this. It's curves. These are called adiabatic process. Okay, so just you split that original reversible cycle into number of adiabatic process, and you remember all the processes are reversible in nature. Okay, don't take irreversible. Reversible process, that's why the most important concept in thermodynamic. Reversible process is one in which all the states are in equilibrium condition. Equilibrium means thermodynamic equilibrium. It has to satisfy mechanical, thermal, and chemical equilibrium. And one more equilibrium is there, that is electrical equilibrium. We are not dealing with electrical part, so we are concerning only about mechanical, chemical, and thermal equilibrium. So after writing this diagram, you have to draw the adiabatic lines. And after that, you can see the top and bottom. Okay, you have to cut this line. Okay, so this is the one line you have to cut at the top, and you have to cut at the top. This is the second line. Third line is this one, and fourth line is this one, and fifth line is this one. Okay, you have to cut the original cycle and reversible adiabatics by these lines. Okay, similarly, you have to cut the cycle at the bottom also. You see this one first line, and this is the second line, and this is the third line, and this is the fourth line, and this is the fifth line. Okay, first step is first you draw x and y coordinate. Then after that you have to draw the original reversible cycle. Then you could draw these curves. Okay, like this, and first and last line, you see it should touch the point of original cycle. Okay, don't show beyond that one. So first and last line, it should touch the original cycle. In between you draw two or three adiabatic lines. You have to cut at the top and bottom by isothermal lines. Okay, so this is how to draw the PV diagram for Clausius theorem. Then once you draw this one, you have to represent. Okay, here it is T1. Okay, isothermal line means it is the T1. Temperature remains same, and here also temperature remains. Next, here you take another cycle. Okay, it's the first cycle I took T1 and T2 as the dq1 is the heat added to the system, and dq2 is the heat rejected from the system. And in second cycle, I took another cycle. Okay, dq3 as the heat added to the system and dq4 as the heat rejected to the system. Now, can you tell what kind of cycle it is? Okay, suppose I'm taking first cycle. Okay, it consisting of two adiabatic process and two isothermal process. First process is isothermal process. Second process is adiabatic process. Next, once again, third process is your isothermal process, and fourth process is adiabatic process. So this cycle consisting of two adiabatic process and two isothermal process. Can you tell what kind of cycle it is? Anybody? Anybody? We already discussed this cycle. What kind of cycle it is?
Sir, Carnot cycle.
Good.
Carnot cycle.
Correct. Good. Okay. So it is Carnot cycle. Carnot cycle I discussed in the previous class. Okay. That's why you have to analyze properly. Okay. Carnot cycle means what? It's not there. Okay, Carnot cycle is it consisting of two adiabatic and two isothermal process. Okay, like that. So this original cycle consisting of number of Carnot cycle. Okay, like that. Whenever you split into this one and you have to draw adiabatic process and at the top and bottom by means of isothermal process. So this is the cycle consisting of number of Carnot cycle. Okay, be careful in drawing the diagram. So it looks like complicated, but it is not complicated. Just you have to start with the circle, any circle. Okay, like this oval shape or circle, whatever it is. Okay, next you draw the adiabatic lines properly. That's why you practice this diagram. Okay, you take one paper and you draw this diagram. Okay, then after that you have to cut at the top and bottom by means of reversible isothermal process. Okay, now I am taking the first cycle. Okay, so T1 is the temperature added, so heat added at isothermal process, and the Q2 dq2, you see the arrow mark. Q1 is heat added and dq2 is the heat rejected. T1 and T2 are the temperature at the constant this one during this process, isothermal expansion and isothermal compression. Similarly, you take another cycle. Okay, so second cycle, so where dq3 is the heat added to the cycle at constant temperature T3, and dq4, you see the arrow mark, dq4 is the heat rejected from the system at constant temperature T4. Like that, you choose just one or two cycles enough and leave remaining the cycle as it is. Okay, to prove the theorem, we are going to take one or two Carnot cycle. Like that, this original cycle consisting of original reversible cycle consisting of number of Carnot cycle. Okay, next you see the theorem. Okay, so it is proved that whenever reversible engine working between source and sink, then the heat supplied and the heat rejected directly related with the source and sink temperature. That is ratio of Q1 by Q2 equals to Q2 by T2. Okay, that is whatever the ratio of Q and T. It is mainly related. Q and T is nothing but our entropy. Okay, that's why we are taking the ratio Q and T in this chapter. So Q1 divided by T1 is always equals to minus Q2 by T2. I can tell. Okay, so some one sign is missed, minus Q2 divided by T2. Okay, why minus? Can you tell me? Actually, sign is missed here. Q1 by T1 equals to minus Q2 divided by T2. What is the significance of minus sign?
Sir, for compression.
Hmm? No, actually Q1 by T1 is this one sign is missed, minus is there. Actually, it should be minus. A minus Q2 divided by T2. Why minus? Why I'm going to put minus? Why not plus? Can you tell me? Anyone? Why minus sign for Q2? Why plus sign for Q1? Already studied sign convention in work and heat transfer. You can you glance sign convention?
Q1 is the heat released and Q2 is the heat absorbed by the engine. Heat.
Correct. So already studied sign convention. Whenever you add the heat to the system, you have to take plus. Okay. Whenever the heat is rejected from the system, you have to take minus. Okay. That's why I said the sign convention for work done and heat transfer are most important. Here we are going to apply all these sign convention in this chapter. Okay. So whenever the heat added, the internal energy increases. So entropy increases. You have to take plus, and whenever the heat is rejected from the system, you have to take minus. Okay, that is heat rejected from the heat engine, okay, to perform the work. Next, you have to shift that term towards left hand side. That's q1 divided by t1 plus q2 divided by t2 equals to 0. Okay, so whenever you take towards this side, so you are going to write the equation as q1 by t1 plus q2 divided by t2. Okay, equals to 0. Like that. Okay, so you can take the second cycle. Then how you are going to write for second cycle? Q3 divided by T3 equals to minus of Q4 divided by T4. Okay, starting I took for first cycle taking the temperature T1 and T2, and now I am taking the second cycle. Okay, where dq3 is the heat added, you can write q3 divided by t3 equals to minus of q4 divided by t4, or q4 divided by q3 divided by t3 plus q4 divided by t4 equals to 0. Like that you can write for any number of the cycle. Okay, first cycle you are writing q1 by t1 plus q2 by t2 as 0. Second cycle you are writing q3 divided by t3 plus q4 divided by t4 as 0. For third cycle, you can take 5 and 6, that is q5 divided by t5 plus q6 divided by t6 equals 0. Like that you can take any number of the cycles, and then finally how we are going to write. Okay, that is you can write this equation. You see, q1 by t1 plus q2 divided by t2 as 0. Okay, q3 plus divided by t3 plus q4 divided by t4 as 0. Like that you can write any number of the cycle. And finally, how we are going to write in this equation is q1 divided by t1 plus q2 divided by t2 plus so on equals to 0. Okay, and this is the algebraic summation of q by t equals to 0. For you see the simple or, always you have to take the reversible cycle. Whatever we are dealing with the reversible process only, keep in mind. That's why even this suffix also most important. Okay, R indicates reversible cycle. That is summation of q by t equals to 0, or cyclic integral of dq by t equals to 0. This is called as the Clausius theorem. Okay, cyclic integral of dq by t is always equals to 0 for reversible process. And we are having one more concept called as irreversible process, where cyclic integral of dq by t is less than 0. Okay, we'll prove that one in the next slide. Okay, cyclic integral of dq by t is always equals to 0. This is called as Clausius theorem. Okay, so whenever they ask sketch and prove, state and prove, Clausius theorem means beginning is this diagram is most important. Don't make any confusion between this diagram. First you draw the diagram correctly, and then you have to write the explanation. Then after that you have to write, you have to consider two cycles, any two cycles you can consider, and then after that you have to write the equation, and finally you are going to write this equation as cyclic integral of dq by t or equals to 0 is nothing but cyclic integral of ds is always 0 for reversible process. That is called as Clausius theorem. Okay, understood guys? Any doubts in this one, Clausius theorem? Okay, any doubts? Once you understand Clausius theorem, then only you can understand the remaining thing. Okay, the first and foremost thing is this analyzation of this diagram is most important. Okay, so you have to analyze. So what you can do better, you take paper and you have to practice this diagram, then only you'll come to know. Okay, after drawing yourself only you are coming to know how, what are the process, and then how to write the sketch and those things. Okay, okay, first time you get wrong thing, don't worry. Okay, just keep on practicing. First you see the diagram and write down. Okay, so then after that, without seeing the diagram, you can practice yourself. First step is you see the diagram as it is, you copy it. Okay, so that will come to know how to draw the diagram, because in thermodynamics the diagrams plays very important role. Okay, so everything you can explain with the diagram only. Okay, once the diagram is wrong, so you lose the mark, especially in PV diagram and TS diagram. You should be very careful. Okay, so for problem also, once you draw the PV diagram, it is very easy to understand and very easy to calculate the things. And the next concept is the most important concept. Okay, in every exam they used to ask this one. Okay, Clausius inequality, I am telling, so one of the important concept in entropy chapter. Maximum time they used to ask this concept. Okay, explain the Clausius inequality for the reversibility of a cycle. Here we are going to prove. Okay, so cyclic integral of dq is equals to t for a reversible process. Cyclic integral of dq by t is less than 0 for irreversible process, and cyclic integral of dq by t is greater than 0 for impossible case. There are three cases are there. Okay, Clausius theorem just tells the cyclic integral of dq by t is only for reversible process. It does not tell about the other process. Okay, in Clausius inequality we are going to prove, okay, three cases. You remember there are three cases. Cyclic integral of dq by t is equals to 0 for reversible. Cyclic integral of dq by t is less than 0 for irreversible, and cyclic integral of dq by t is greater than 0. It is not possible at all. How we studied PMM1 and PMM2, like that cyclic integral of dq by t is greater than 0 is impossible. It is always less than 0 or exactly equals to 0. That is the proof we have to do. Okay. Clausius inequality. Heading is Clausius inequality. Once again, first you analyze the diagram. Okay. This is the temperature volume diagram. Okay, so x coordinate, x coordinate as volume and y coordinate as temperature. Okay, don't worry about this uh, coordinates. So concentrate mainly on this nature of curve. Okay, so here first you draw one horizontal line at the bottom. Okay, so you see, first you draw one horizontal line at the bottom, and then you write one curve in this way. Okay, AB as a curve. You have to write like this. First step is, first you draw one bottom line, straight line. Next you have to draw the curve AB. And once you draw AB curve, then you see you have to write the number of adiabatic curves. You see 1, 2, 3, 4, 5, 6. Like that you can write any number of the curves, no problem. But you have to draw in this way only. Okay, and you remember there are two curves. Okay, it should pass through the points A and B. The first and last one should pass through A and B. Okay, don't write away from these 2 points. So the first and last should pass through the points A and B, and in between you have to draw some 3, 4 adiabatic curves. Okay, and then here in the previous case we studied all reversible case only. In this case we are going to study one of the irreversible process. Okay, so AB. Okay, join AB like this. Okay, forward, and this one you can join AB with a dotted line. Dotted line indicates your irreversible process. Okay, and all the continuous line represents the reversible case, and irreversible process is represented by dotted line. Okay, and all the states are not in equilibrium condition in case of irreversible process. Okay, first and foremost thing is your diagram. So better once again you practice this diagram. First bottom line, then you draw one curve AB, then number of adiabatic curves, and then after that you have to cut at the top. See, only at the top, okay, not at the bottom. Okay, so bottom is T2 only. Only one line is there, but only at the top you have to cut the number of isothermal process. Okay, for all the process. Okay, this is 1, this is 2, 3, 4, and 5, like that. Okay, so you have to cut only at the top. Okay, now here this is about diagram. Okay, cut only at the top isothermal process. Anyhow, the bottom is common. Okay, for all the process. Okay, and we are going to cut only at the top. And these are all temperature lines. This is also constant temperature line. Okay, these are the constant temperature lines for individual cycle. And what we are taking is the common for all the cycle. And you have to Write the AB is general process, and this one is T2, and you can write like this. Okay, so even labeling also most important. Now you see, mark the point as A, B, C, and D. So first and last point you mark as B, and these 2 points you mark as C and D. Okay. So let ABCD is a cycle because initial and final states are same. Let us consider ABCD as a cycle, just cycle. Yeah, in this cycle, AB is a general process. Okay, I can take it as reversible or reversible, assuming. Okay, say starting, I'm assuming. Okay, it may be any general process. Okay, and this cycle is divided into number of Carnot cycles. Okay, I'm saying this is a Carnot cycle only. Okay, because we are having two adiabatics and two isothermal process. Okay. Let the cycle is divided into number of elementary cycles. Okay, and we know that the efficiency of any cycle is given by net work done divided by heat supplied. Okay. Net work done is nothing but heat added minus heat rejected divided by total heat supplied. Okay. And you see, so dq I am taking as the heat added to the cycle, and dq2 is the heat rejected. You analyze the notation, dq is the heat added and dq2 is the heat rejected. So according to our formula, efficiency is given by dq minus dq2 divided by dq, or you can write eta equals to, eta is efficiency, 1 minus dq2 divided by dq is the efficiency of this cycle, where dq is the heat supplied at temperature T and dq2 is the heat rejected at temperature T2. So you have to write a dq2 and T2. dq is the heat supplied at temperature T and dq2 is the heat rejected at temperature T2. Okay. And we proved that the efficiency of a general cycle is always less than the efficiency of a reversible cycle. Okay, we proved in Carnot theorem that the reversible cycle is the one which gives the maximum efficiency, and general cycle, suppose you take, the efficiency of general cycle is obviously less than the efficiency of a reversible cycle. Okay, that's why I say Carnot theorem is most important theorem, where we are taking different cycles and we proved the efficiency of reversible cycle is always maximum value. Okay? And general, they say whatever n is, eta is general, is less than or equals to eta reversible. So you can write either less than or equals, but it never greater than reversible cycle. So you can write in the statement eta is less than or equals to eta reversible, and eta generally is, we wrote that 1 minus dq2 divided by dq. Just now this is the efficiency of general cycle. Okay, is less than or equals to 1 minus dq2 divided by dq reversible. Okay, so no change in the equation, only you have to add the term reversible. Okay, first one indicates your general cycle and second one indicates your reversible cycle. Okay, the formula is same, but statement is most important. The efficiency of general cycle is less than or equals to the efficiency of reversible cycle. It never greater than the reversible cycle. That is, eta generally is 1 minus dq by 2. Because we are not mentioning any term, means it is a general cycle only, less than or equals to 1 minus dq2 divided by dq reversible. Just you add the suffix reversible. The formula is same. Okay. Or we can write. Okay. So here I am neglecting the term 1 in both the equation. Okay. How I am going to write? Minus dq by t divided by dq is less than or equals to minus of dq2 divided by dq reversible. Okay. Here what I am doing to, just I am neglecting the term 1 on both sides, and except 1 you write the remaining equation. Minus dq2 divided by dq is less than or equals to minus of dq2 divided by dq for reversible. Okay, and suppose in order to write the greater than formula, okay, how you are going to write? Okay, this is the step you have to understand very carefully. Okay, so here d minus of dq by t is less than or equals to minus of less than or equals to minus of dq2 divided by dq reversible. Whenever you change the sign, okay, so I want to change the sign minus on both sides. So you can write dq by 2 divided by dq is greater than or equals to, don't write minus less than or minus less than or equals, you have to write greater than or equals. That's why I said this step is most important. Okay, so whenever you are changing the sign, you have to write dq2 divided by dq is greater than or equals to dq2 divided by dq reversible whenever you put the sign. Okay, otherwise you take one number. Okay, so minus 2 is less than or equals to minus 1, like that you can take, so you'll come to know. Okay, so you better you take one number and you come to know. So whenever you change the sign, dq2 divided by dq is greater than or equals to dq2 divided by dq reversible. Okay. Now once again I'm taking dq divided by dq. So you can change the, you see here starting the numerator is dq2 and denominator is dq. Now I'm changing the terms. Okay, dq I'm putting in the numerator and dq2 I'm putting in the denominator. Whenever you're changing the numerator and denominator, once again you have to change the symbol. Instead of greater than, you have to write minus. So we should be very careful in this one only. So try to understand these three steps. Okay, once these steps are understood, okay, nothing is there in this theorem. Okay, dq2 divided by dq is greater than or equals to dq2 divided by dq reversible cycle. First one indicates general cycle. Whenever you change numerator and denominator, okay, you have to change like this. Okay, for example one you take. Okay, 3 by 4 is greater than half. Okay, better you take like that. 3 by 4, suppose I am taking 3 and 4 is greater than half. Okay, that is 75% is greater than 50%. You take one number, 3 by 4 is greater than half. Suppose if you change the numerator, in that case you have to write 4 by 3 is less than 2. Okay, so same formula. Okay, we can apply. Okay, I am taking 3 by 4 is greater than 1 by 2. Okay, suppose if you change the number, 3 by 4 means 4 by 3, you can change 4 by 3 is less than 2. Okay, like that you can analyze. Hope you understood that equation. Okay, whenever changing the numerator, you have to change the greater than symbol into lesser than symbol. Okay, better you take 3 by 4 is greater than 1 by 2, or 4 by 3 is less than half. Suppose you change the numerator, it becomes 2. Okay, so 4 by 3 is less than 2, like that you can take. Okay, so next step, for reversible cycle, we know that dq divided by reversible means always it is proportional to t. You can take the next term. Okay, dq divided by dq to reversible is t by t2, because dq is proportional to t and dq2 is proportional to t2. So you can write, okay, dq by t2 is nothing but dq2 divided by t2, or you can write dq divided by dq2 is nothing but t and t2. q is proportional to t and q2 is proportional to u. Okay, now you have to substitute the value of dq divided by dq2 t divided by t2 in above equation. Okay, just you are going to replace. Don't do anything. So only these three lines are most important. Okay, so dq divided by dq2 is nothing but RHS term. Instead of this one, just you write t divided by t2. Okay, and then just you change the terms. dq, so you take it is a numerator, you take as a denominator of dqc. Just you interchange the term. dq divided by t is less than or equals to, and whatever dq is there, just you take as a numerator. Okay, there is no change in equation. Okay, dq divided by dq2 is less than or equals to t by 2. Now you take t as the denominator of dq is less than or equals to dq2 divided by t2. And whatever this equation is proved for any general process AB. Now we took starting, we consider for general process AB. It may be reversible or it may be irreversible. Okay, just starting with that. But for reversible process using the Clausius theorem, that is ds divided by dq by t is never than less than less than. Okay, always it is equals to dq divided by t and dq2 divided by t2. So So for irreversible process, dq by t. So for any general process, you see this is the summary how we are going to write. dq by t is less than or equals to ds. dq by t is nothing but ds. This is a standard formula. Okay. So dq by t is less than or equals to ds. Okay, this is a formula. We know that dq by t is less than or equals to ds for any process. If you remember, it may be uh, a reversible process or irreversible process. And for suppose you put the cyclic integral on both sides. Okay, cyclic integral of, just you add the cyclic integral symbol on both sides. Cyclic integral of dq by t is less than cyclic integral of ds for cyclic process. Just you put the cyclic integral. But we know that cyclic integral of ds is 0 because ds is the property. Hence, this term is 0. Okay, because S is the property, entropy. Cyclic integral of any property is 0. And finally, we can write it as cyclic integral of dq by t is less than or equals to 0. In Clausius theorem, we proved cyclic integral of dq by t is exactly 0. And in Clausius inequality, we are going to prove cyclic integral of dq by t is less than or equals to 0. It never greater than 0. You remember, that's why we consider general process AB. And in Clausius theorem, we consider only the reversible cycle. Okay, based upon this one. So this is the most important. Okay, so what these are the 4 lines are there. No, these are the most important equation. First equation you see, cyclic integral of dq by t is less than equals to 0. It is called as Clausius inequality. It's a general equation. And based upon these three, we are having the 3 condition. First condition is cyclic integral of dq by t is 0. So cycle is possible, and this is for reversible process. First case. This is the first one is Clausius inequality, and based upon that one, we are going to prove whether cycle is possible or not, or whether the process is reversible or not, like that. Cyclic integral of dq by t is 0. Cycle is possible and the process is reversible. Second case, cyclic integral of dq by t is less than 0. This is called as the Clausius inequality for a irreversible process. Only, and third final is final condition. This is the most important thing. Cyclic integral of dq by t is greater than 0. It is not mentioned here actually. Cyclic integral of dq by t is greater than 0 is not possible. Let a cycle never exists. Okay, we are having only reversible or irreversible, and this is the Clausius inequality. If exactly 0, cycle is possible and reversible in nature. If it is less than 0, the cycle is possible and irreversible in nature, and cyclic integral of dq by t is greater than 0 means cycle is not possible at all. Okay, so whatever the things I covered in today's class, Clausius theorem and Clausius inequality, the most important concepts in the entropy chapter. Okay, maximum time they used to ask this Clausius inequality for 10 marks. You remember, that's why go through the diagram properly, go through the derivation properly. Okay, still if you have not understood, you can ask me. Okay, so I'll stop the session now. Okay. Understood, guys? This derivation, most important derivation, Clausius inequality and Clausius theorem. Okay, suppose if you are having any doubts, you can ask me. Okay, you can clarify, because these are the 2 important concepts in entropy. Okay, maximum time, 90% of the time they used to ask this Clausius theorem. Okay, and Clausius inequality, and whatever derivation I did. Okay, for all the 5 process. So all of you enter your USN in the chat box. Okay, I'll consider for attendance. Those who are not entered, please enter in the chat box. Okay. Okay, I'll stop the session now. So those who are not entered, please enter.